The F-14 Tomcat swing wings weren't designed to make it faster. They were engineered to solve a problem that almost killed American carrier aviation: how to defend the fleet from Soviet bombers launching cruise missiles 300 miles away while still being able to land on a moving carrier deck at night. Every other solution failed. Variable geometry was the only answer that worked. In 1960, the Navy faced a nightmare scenario. Soviet Tu-95 Bear bombers could launch AS-4 Kitchen cruise missiles from beyond the range of any carrier-based interceptor. By the time F-4 Phantoms got close enough to shoot, the missiles were already inbound toward the carrier battle group. The fleet needed an aircraft that could patrol 500 miles from the carrier, carry massive long-range missiles, and still operate from a pitching deck in the Pacific. Fixed-wing designs couldn't do it. The F-14's swing wings weren't about speed. They were about surviving contradictory aerodynamic requirements that would have grounded any conventional aircraft. Here's the engineering reality most people miss. Landing on a carrier requires slow, stable flight with maximum lift. You're coming in at 135 knots with the deck moving 30 feet up and down. Miss the wire by 6 feet and you're swimming. But intercepting Soviet bombers 500 miles out requires sustained supersonic speed while carrying 6 Phoenix missiles weighing 1,000 pounds each. Those are opposite aerodynamic demands. A wing optimized for one condition fails catastrophically at the other. The F-4 Phantom proved this limitation. Excellent fighter, but its fixed delta wing design forced compromises. Landing speed was 145 knots, dangerously fast for carrier operations. It needed maximum afterburner just to get airborne with a full weapons load. And cruise efficiency was terrible. An F-4 burned so much fuel getting to station that loiter time was measured in minutes, not hours. The Navy needed an aircraft that could fly out 500 miles, patrol for hours, engage multiple bombers, and still have enough fuel to land back on the carrier. The F-4 couldn't do it. Something had to change. Variable geometry wings solved this by changing the aircraft's aerodynamic profile in flight. At 20 degrees sweep, the F-14's wings are nearly straight. Maximum surface area, maximum lift at low speeds. This configuration generates enough lift to land at 135 knots with full control authority. The pilot can see the deck, make corrections, and catch the wire with precision. But sweep those wings back to 68 degrees, and you're looking at a completely different aircraft. The wing area drops by 40%. Drag decreases dramatically. Suddenly, the same aircraft that lands gently on carriers can accelerate to Mach 2 and maintain supersonic cruise. Here's where the operational advantage becomes clear. The F-14 could launch from a carrier, sweep wings forward for fuel-efficient cruise, fly 500 miles to station, loiter for 2 hours with wings at optimal sweep for endurance, detect Soviet bombers at 195 miles with its AWG-9 radar, sweep wings back for high-speed intercept, fire Phoenix missiles at targets 100 miles away, then return to the carrier with wings forward for landing. No other carrier aircraft could execute this mission profile. The swing wings weren't a feature. They were the entire concept. But here's the capability that justified the complexity. The F-14 could engage 6 targets simultaneously with Phoenix missiles while those targets were still 100 miles away. Soviet doctrine called for mass bomber raids. 20 or 30 Tu-95s launching cruise missiles in coordinated waves. One F-14 could break up that entire raid before missiles were released. 2 F-14s could defend an entire carrier battle group. That capability existed because variable geometry let the aircraft carry 13,000 pounds of missiles while maintaining the flight characteristics needed for carrier operations. Fixed-wing designs that could carry Phoenix couldn't land on carriers. Designs that could land on carriers couldn't carry Phoenix effectively. The F-14 did both. The engineering gets more impressive when you understand the Soviet threat profile. AS-4 Kitchen missiles had a range of 300 miles and flew at Mach 4.6. Once launched, Intercept was nearly impossible. The only defense was killing the bomber before missile release. That meant F-14s needed to patrol far from the carrier, 400 to 500 miles out, and maintain station for hours. Fuel efficiency was critical. Here's the technical reality. At 68 degrees sweep, the F-14 burns 40% more fuel than at optimal cruise sweep of 45 to 50 degrees. But at 20 degrees, drag increases and efficiency drops again. The wings automatically adjusted in flight to maintain optimal efficiency for current speed and weight. The aircraft could patrol for 3 hours at 400 miles from the carrier. An F-4 Phantom would be out of fuel in 90 minutes at the same distance. Watch what happens when you combine this with the weapon's capability. Each Phoenix missile weighs 1,000 pounds and creates significant drag. Carrying 6 of them under fixed wings would increase drag by 60 to 80%, destroying range and endurance. But the F-14's swing wings allowed the missiles to be mounted on special pallets that worked with the variable geometry. As wings swept back, the pylons rotated to maintain optimal airflow. As wings swept forward, pylons adjusted again. This meant the F-14 could carry 6 Phoenix missiles with minimal drag penalty across the entire flight envelope. Soviet bombers had no equivalent capability. The operational reality changed naval warfare. Before F-14, carriers operated with defensive fighter patrols maybe 200 miles out. Soviet bombers could launch from 300 miles and turn away before intercept. After F-14, the defensive perimeter expanded to 500 miles. Soviet bombers had to penetrate much deeper into defended airspace to launch missiles. That meant longer exposure to F-14 patrols, higher risk of intercept, and reduced effectiveness of mass raids. The swing wings enabled this strategic shift. They weren't about making the F-14 faster than the F-4 in a drag race. They were about maintaining station 500 miles from the carrier with enough fuel to engage threats and return safely. Now combine that with carrier deck operations. Carriers have limited deck space. Every aircraft represents a trade-off between capability and footprint. The F-14, with wings swept forward, took up 64 feet of deck space, nose to tail. With wings swept back for storage, it dropped to 62 feet, but width was the critical factor. Wings fully forward, 64 feet wide. Wings fully swept, 38 feet wide. That 26-foot difference determined how many aircraft could fit on deck. More F-14 meant better fleet defense. The variable geometry directly increased sortie capability by allowing tighter deck spotting. Fixed-wing aircraft with equivalent capability would have been too large for efficient carrier operations. Here's why adversaries couldn't replicate it. The Soviet Union built swing-wing aircraft, the MiG-23, the Su-24, but these were land-based designs without the carrier operation requirement. The engineering tolerances for carrier-based variable geometry were exponentially more demanding. The wing box, the structural component that bears all flight loads and allows wing rotation, needed to withstand catapult launches, arrested landings, and extreme flight loads while maintaining precise sweep angles. Grumman engineers spent years developing the F-14's wing box. It weighed 1,800 pounds and cost as much to manufacture as an entire F-4 Phantom wing. The Soviets never solved this engineering challenge for carrier operations. Their only carrier-based fighter was the fixed-wing MiG-29K. But here's the technical reality that eventually killed variable geometry. Complexity equals vulnerability. The F-14's wing sweep system included hydraulic actuators, mechanical locks, electrical systems, and computerized controls. All of these required maintenance. The wing box was a wear item. Structural fatigue from repeated cycles eventually grounded aircraft. Modern fixed-wing designs using advanced materials and computer-controlled flight surfaces can achieve similar performance without the mechanical complexity. The F-18 Super Hornet replaced the F-14 with fixed wings by accepting some capability trade-offs while dramatically reducing maintenance requirements. Yet the F-14's swing wings accomplished something no modern fighter can replicate exactly as configured. They solved contradictory requirements through elegant engineering rather than compromised performance. The aircraft could land at 135 knots and intercept at Mach 2. It could loiter efficiently at 400 miles and sprint at supersonic speeds. It could carry massive weapons loads while operating from carriers. Modern fighters achieve these individually through different means, but the F-14 did all of them simultaneously because its wings changed shape to match mission requirements. The strategic impact lasted decades. From 1974 to 2006, F-14s defended American carrier battle groups against threats that would have overwhelmed earlier fighters. The aircraft shot down Libyan fighters, provided air cover over Iraq, and maintained fleet air defense during the Cold War. Soviet planners knew that attacking a carrier defended by F-14s meant facing Phoenix missiles at ranges where their own aircraft had no counter. The swing wings weren't the weapon, but they enabled the weapons platform that changed naval aviation. This is why modern fighters abandoned variable geometry despite its advantages. The F-22 and F-35 use fixed wings with computerized flight control. They achieve efficiency through thrust vectoring and adaptive flight surfaces instead of changing wing sweep. The maintenance burden of mechanical sweep systems outweighs the aerodynamic benefits when modern materials and computers can compensate. But in the 1970s, variable geometry was the only solution that worked. The F-14's swing wings were really for solving an impossible problem, defending the fleet from Soviet bombers while operating from carriers. They succeeded because Grumman's engineers refused to accept the compromises that doomed every other design.